Hello, welcome to Infinity Geospatial. This is a YouTube channel I created to help undergrads to familiarize themselves with anything geospatial, anything geoscience. My name is John Osukundia. I am the CEO of Goodwill Geospatial Consult. Today, I'm here to take you through an introductory lecture on remote sensing and purposely its application in mineral mapping. This is the outline of the presentation. We're first going to focus on what we mean by remote sensing and the phrase remote sensing in a layman's perspective. Secondly, we are also going to know the technicalities when we mean by remote sensing. Then we head way to the applications of remote sensing, core component of remote imaging, the number of satellites, their applications, and their functionalities, and also the images they capture. We are also going to zoom into the concept of spectroscopy, how materials absorb and emit radiations, and also the black body effect, principally focusing on how to map materials based on their thermal signatures or their thermal variations. Then also look into understanding the electromagnetic spectra, spectral resolutions of satellite images, how to do spatial enhancement on our satellite images, what we mean by spectral signatures, what we mean by spatial enhancement and how to do the spatial or spectral enhancement, and how to assess the uniqueness of end members in a satellite image based on their spectral signatures. And lastly, the third segment will focus on doing a bit on mapping, how to understand what we mean by mapping, how to detect objects in satellite images, what are the types of or the number of algorithms and how they operate in helping us to detect objects in our satellite images, the sources of satellite images we can get them, the satellite data processing and licenses, how to process our satellite images, and the software licenses we need in order to process our satellite images. What is satellite image or what is remote sensing, as one may ask? In a layman's perspective, remote means that having something without making physical access to it or without having physical access to it. That is what we call remote. So put it in this context that you want to get a phone, you've seen a phone online on Walmart online portal, and you want to get a phone for your own usage. Maybe you are in a different location, different from Walmart, and you want to get that phone. All what you have to do is that create an account on Walmart website, log in, fill your details, input your credit card details, make purchase, input your shipping details. Then voila, the items or the phone will be shipped to you without you having to go to Walmart supermarket to get your stuff. So that is what we call remote, the term remote. Now sensing comes in an idea of acquisition, collection, how to get access to something, what you require in order to do it. Now, how do you buy from Walmart remotely? You need the internet, you need a computer or a phone, you need a website, and you also need a website that serves as a user interface between you and Walmart. So these are the sensing mechanisms you need in order to undertake the remote process of buying from Walmart. So in layman's term, you want to get something from somewhere but without having access to it. So remote sensing practically involves that in a layman's perspective. So now let's come to the technical definition of remote sensing. Remote sensing is a type of spatial technology. When we say spatial technology, it's about monitoring a phenomenon in an area without having physical access to it. So we monitor phenomenon in an area. That's it. So it's all about monitoring. Spatial technology is all about mechanisms in monitoring. So it's a type of spatial technology that samples emitted and reflected electromagnetic radiations from the Earth's terrestrial, atmospheric, and aquatic environment in order to detect and monitor variations in physical objects without having access or physical access to it. Now, this method of data collection, remote sensing is all about data collection, typically involves the aircraft-based and satellite-based sensor technologies. So these sensing technologies or sensing media have been stratified in two folds. Thus, we have the passive sensing and the active sensing devices. So we call them sensors. So passive sensing or passive sensors rely on external stimuli to gather radiations that is reflected or emitted by an object or the surrounding space. The most common source of these radiations that are used by passive remote sensors is the reflected sunlight, the reflected radiations from the sun. Now, on the other hand, passive sensors rely on internal stimuli to collect data, that's emitting energy in order to scan objects and areas, whereupon a sensor measures the energy reflected from the target. That's take particular example as your mobile phone. You take pictures with your mobile phone, no matter the times of the day, whether it's dark or there's sunlight out there, you can take pictures in even in the dark places. So it means that your phone has an internal mechanism that generates light to support the camera in order to capture the images you want. Typical example of active sensing devices are the lidar and the radar sensing tools. Now let's look at the remote sensing process, specifically the passive remote sensing process. The passive remote sensing process will require an external source of energy or an external source of stimuli. So this here is our sun. Our sun generates an external source of stimuli in the form of solar radiations. These solar radiations have a bipolar component. They have what you call the magnetic fields and electric fields. They also have a third component that is what you call the energy aspect of it, the temperature or the heat aspect of it. So here we have the sun radiating energy to the earth's surface. This energy locates or strikes on an object on the earth's surface here. The object, due to its chemical constituents or crystal behavior, absorbs some of the radiations and also reflects some of the radiations. Now, these reflected radiations here, a proportion or some proportions of the reflected radiations go back to the sensor to be recorded. And once the sensor captures those reflected radiations, now you should know that the reflected radiations that get to the sensor is what we call the emitted radiations. It's what gets to the sensor to be recorded, the emitted radiations. Now the reflected radiations have two components. Some of the radiations, after the object or the material has absorbed some of the energies coming from some of the radiations coming from the sun, it reflects the residuals. Now the residuals, part of the residuals get to the sensor as emitted energy and part are scattered in the atmosphere. They are loitering in the atmosphere. So those loitering in the atmosphere cause what we call an albedo effect. So now the emitted radiations that are captured at the sensor level are transmitted to a processing workstation where it will be worked on, applied various computation mechanisms to get an image readily accessible and applicable to our world or for our usage. So the image here is also another interpretation of the passive remote sensing process, and these are the area of work or the areas we can apply the satellite or the remotely sensed images. Now we are looking at the applications of remote sensing. Where can we apply remote sensing? The first point of call as geoscientist, as a geologist, is I will put regional mapping on top. That's regional, mineral, and lithostructural mapping, where we can map minerals, we can map rocks, and we can map structures. That's basically what geologists need. Yes, basically we map rocks, we map structures, and we map minerals. Not necessarily minerals, we map mineral alterations. Yes, we map minerals and their alteration associated with them. Then the second point is the vegetation analysis, hydrogeological studies, shoreline analysis, geospatial-temporal studies, environmental monitoring. That's we want to look at how our environment has transited through time. You wouldn't tell me that the state of your environment as it is now was the same state as it was 50 years ago, 10 years ago, 20 years ago. Things have changed, our environment have changed. There have been inception of new mechanisms in the environment that is affecting our environment to a large scale. So we can rely on this remote sensing, the benefits of remote sensing, to also quantify the extent of change that has occurred in our environment from time 1 to time 2, or time T1 to time T2, or variance of time. Now, for geospatial or spatiotemporal analysis, and zoom into what we call the change detection. We are detecting the changes that has occurred through time. For example, urban growth and desertification studies. The next in line is geohazard risk and susceptibility studies. We can map certain geohazards like earthquake, landslides, liquefaction, slope failures, flood. We can map all these things using remotely sensed images. Then LULC, that's land use land cover studies, where we can map the change in our land with respect to time. Ocean studies, thermal analysis. This is a vital component of remote sensing for mineral mapping. Thermal analysis. We are going to briefly discuss this in the subsequent segments. Then geomorphological studies. Geomorphology, we are looking at the changes in our landscape with respect to time. Our landscapes have evolved through time. So, and there are various agents that aid in the changes of our geomorphology, the geomorphology of our landscapes. So remote sensing can be used in order to scale out the effect or to identify the component that is controlling these geomorphological changes. These are also other forms of the images here are other forms or other areas where we can apply remote sensing for biogeochemical heterogeneity studies, to develop biodiversity models, for inventory of biodiversity mechanisms, for aquatic or habitat studies, and environmental or vegetation health studies. Now we look at the core component of remote imaging. For remote imaging, all what we know or what we have to do is we check first the expertise, check secondly the technology involved, and the platform for us to get our images. Now the expertise has the precedence of intelligence or knowledge you have to get in order to venture into remote imaging. You need a knowledge, a practical knowledge in airborne hyperspectral surveys. You also have to have an in-depth knowledge in machine learning. This is a new field that's coming on board and it's really fascinating. The next is image processing, how to process image using computational mechanisms. Then we also go into geocomputation, how the structure or the surface of the earth is affecting the capturing of our images, how to integrate these shape of our earth into the concept of our image. The image we acquire will be in rectangles, but our earth is in a spherical shape. So how do we split our earth into a cylindric? We split our earth into a splitted cylinder, then we dissect the images or superimpose this split on our images to make better interpretations. Then a foreknowledge in quantum physics and string theory, principally on the concept of photoelectric emission. Then the last is thermodynamics, as radiation, the concept of radiation and blackbody effects. You have to have an in-depth knowledge in that. Now the technologies, we have the hyperspectral, multispectral, the radar and the thermal imaging, and cloud processing analytics. The platforms we use are satellites, airborne monitoring mechanisms, and unmanned aerial vehicles, drones and spectrometers. For the satellite imaging or satellite image capturing, it's principally a passive remote sensing process. The types of satellite images. We have the multispectral. This is a public image where we can acquire them. They are free of charge. It's been paid for by various government institutions like NASA and Copernicus, that's the European Union. These images can be acquired. They are free of charge. You can acquire them for different number of times, in a different day, in different times, for different years. You can acquire them. So for the Landsat series, that is a multispectral image, we have the Landsat thematic mapper, we have the Landsat enhanced thematic mapper, we have the operational land imager, a thermal infrared radiometry, that's the TIR. As for the Landsat series, then we also have the ASTAR. The ASTAR is also a multispectral imaging platform. The full definition for ASTAR is Advanced Spaceborne Thermal Emission Radiometry. Then you have the Sentinel series. Sentinel is by the European, sponsored by European Union. Then the next phase of the satellite images are the hyperspectral images. These are commercial. You have to pay bodies or institutions to use their sophisticated technologies to come and capture those images for you. In the next slides, we are going to know the distinction between hyperspectral and multispectral images, and also going to look at each and every platform or the image platform and the type of images we can get and what they do for us. For the hyperspectral images, they are commercial, so you have to pay huge sums of money to consultants or to companies that are well versed in using the hyperspectral technology to capture the images for you. So for the hyperspectral, we have the Hyperon, we have the Iconos, Avaris, we have the Joy, the many others. So these are the satellites we have. For the ones above here, they are the multi-spectral. They are publicly available images. Then the hyperspectral, you have to pay to get them. So for the multispectral, we have the Landsat 1 and 2, we have the Landsat 3, Landsat 4 and 5, Landsat 7, Landsat 8, Sentinel 1, Sentinel 2, then ASTAR data. So on the extreme right side, we look at the number of days the satellites use to complete one image capturing around the Earth. It uses 18 days for us for Landsat 1 and 2. The satellite technology have been designed that it revolves or it rotates around the Earth to capture the images or complete rotation, one complete rotation over the total Earth area in 18 days. But this has been reduced to 5 days in Sentinel-2. So it looks like for every 5 days, Sentinel gives us one full image of the Earth. That's what it means. So it means that these satellites are running on a hyperspeed and they take very quality images. So that's that. Then when you look at a hyperspectral, where spot 1 to 5 takes 1 to 3 days to capture one satellite, one spot, one satellite. Takes 1 to 3 days to capture one full complete image of the Earth. Then Joe takes 1 day. Even Pleiades takes less than a day to make one complete image of the whole Earth. That's very fascinating. Now the next is, let's look at satellites in orbit. These ones are passive satellites in orbit. This is a legend here. The yellow demarcates satellites that are in formulation. They are now being developed in the labs. So it's a concept that's coming on board, not necessarily practicalized, but they are formulating them to come into inception. So the yellow indicates a formulated satellite. The orange coloration here indicates satellites that are being implemented or they are being used to capture images, currently being used. The green are for primary operation of satellites in primary operation. So we can see Landsat 8 is in primary operation. It's operating at its primary level. It has not got an enhanced capability. So then the pale blue color is for satellites that have extended operations. That their mode of operations have been enhanced. So particularly for Landsat 7, Landsat 7 have been upgraded to add other vital operational mechanisms to it. So that's all that. Now we delve into the concept of spectrometry or spectroscopy. Sorry. What do we mean by spectroscopy? Spectral means that a window of radiations. That's what we call spectra. It's a window of radiations. So we are measuring the wavelength of radiations across a specified window. That's what we call spectra. Now, this is our emitter. For our emitter, let's take we are in the passive remote sensing process. So we have an emitter, which is our source of radiations. That's typically from the sun. The sun has three components, but one is bipolar. That is the electromagnetic radiations. It also has the heat component of it. So these radiations are coming in conjunction with heat. So these electromagnetic radiations that has electric fields and magnetic fields, they hit on the sample. Now, due to the molecular structure of the sample, it emits some of the radiations and also absorbs some of the radiations. The proportion of the emitted radiations is a function of the proportion of reflected radiations. Now, it should be noted that not all the emitted radiations or not all the reflected radiations get to the sensor. some are scattered in the atmosphere to create what we call the albedo effect. So whatever the sensor captures is a proportion of the reflected radiations, which is what we call emitted radiations. Now let's come to the term we are going to predominantly use in this phase is absorption and emission. When we say absorption, what does it mean? For absorption, just as all it's well, and we all know in atomic physics, or yes, atomic physics, we've dissected atoms, we know electrons exhibit quantized energy levels. So in the ground state it's an energy level 1, then move to the next orbital, it's an energy level 2. Then for each energy level, the electrons are spinning at an angular momentum. Then we have the electron spinning directions. So when an electron is in its ground state and moves to an excited state means it's moving to a higher energy level. So it means that the electron has been quantized, Now, what do we say by quantized? Quantization means that you need energy in order to propel an electron from the ground state to the excited state. You need an energy to excite the atom for its electrons to move from the ground state to the excited state. Now, when the electron is in the ground state, the orbital is close to the nucleus and there is lots and lots of what? Attraction. So how do I get these electrons in the atom from the ground state to the excited state? I have to use energy, bombard it with what? Energy. So that's what it does. The material, due to its molecular structure, releases energy, then material captures it. Now let's look at emission. What do we say emission? Emission is just a liberation of energy. You are moving from an excited state to a ground state. What do we need in order for us to move from an excited state to a ground state? One principle is what you call potential energy or potentiality. So when an object is at a height different from its datum, it has the tendency to fall back to its datum and in the process releases energy. So when an atom is excited and gets down to its ground state, or an electron in an atom is excited and it gets down to its ground state, it releases energy. So absorption means that the sun is incidenting energy on the material. So the material also behave in such a way that it occupies those energy. Now for an emission, once the atoms in the material have occupied or absorbed some level of the energy or the radiations coming from the sun, it will tend to liberate the residual energy. And the residual energy is what we call the energy effect. It has the energy effect. It liberates energy. So the emitted radiations holds the energy. Now this energy comes in various wavelengths. So the function of the spectrometer here is to collect these energy that are in packets. Let's say packet of energy called what? Photons. So the spectrometer measures these photons and records them here. That's the whole principle of spectroscopy. So once you understand this, the remote sensing process becomes very easy for you to get your head around. Now, this is also another concept of spectroscopy in remote sensing, practically in remote sensing. So the sun energy here, which holds solar radiations, which has a bipolar component and a heat component. The bipolar component is the electromagnetic component. So its incidence on the earth surface, on the material on the earth surface, let's say tree or cars or wood or rocks. These materials, based on their molecular structure, their inherent crystal behavior, absorb some of the energy and reflect some of the energy. It should be noted that the reflected radiations, it's not necessary that all the reflected radiations get to the energy, they get to the sensor. The proportion of reflected radiation that gets to the sensor is what we term as the emitted radiations. So the leftover reflected radiations are scattered in the atmosphere and they are what we call albedo. They are albedo. They create an albedo effect in the atmosphere. We are going to focus, or we are going to understand the concept of albedo when we get to thermal imaging. Principles of absorption and emission of a black body. Now, some materials have the inherent property to absorb all the radiations that are incidented on it. Once you incident a radiation on an object, depending on its crystal behavior or molecular behavior, it has the tendency, sometimes it has the tendency to absorb all the energy in it. And conversely, some materials also have the energy to reflect or to emit all the energies incident on them. And these bodies are what you call the black body. They create an effect termed as the black body effect. So a black body is an hypothetical object, that's a perfect object that virtually absorbs all incident radiations at any wavelength. They do not only absorb all radiations, but they can also emit all radiations that is incident on them. Now, a black body obeys what you call the Planck's law. A black body obeys what you call the Planck's law. There is no perfect black body on earth, or there is no body or object that obeys the black body rule, but it's a hypothetical body. But some objects or some materials have relative behavior to a black body effect. An example is quartz. We are going to look at them in the next slide. Now, this is a proportion of radiation intensity, a graph of radiation intensity against the wavelengths. You know, the sun energy is coming as a light, and light has two components. It has the energy component and the wave component. So it has a particle component and a wave component. That's what we call the wave particle duality of light. Particles behave, waves or materials or light behaves as a particle and also as a wave. So that's what we call the wave particle duality. So if the material is a wave, or the radiations coming from the sun is a wave, then it means it has a wavelength. And from the law of photoelectric emission, we have to know the intensity of the radiation. Now, the intensity of the radiations will determine the emission rate, not the frequency of radiation, but the intensity of radiation will determine the frequency rate. But the energy of the radiation is a function of the Planck's constant times the frequency of radiation. So this is a curve for a black body. So the black body exhibits a perfect symmetry in function of radiation and wavelength, but there is a body that behaves synonymous to a black body but to some effect, and that's quartz. Quartz is not a perfect black body, but at some wavelengths behaves like a black body. So on this side is the radiation intensity against the wavelengths. So you can see once the wavelength is increasing, these are characteristics of some of the materials, and this intensity is a reliance or as a function of the temperature. The intensity of radiation is a function of the temperature. Now this here is the Planck's law. It says that the intensity of a radiation is a function of the wavelength and temperature, where h is the Planck's constant, c is the speed of light, and T is the temperature of the radiation. The I is what you call the power per area per solid angle per wavelength, mostly expressed as the intensity of radiation. Then the K here is the Boltzmann's constant. So once you are able to compute this, you can know the intensity of your radiation or the power per area per solid angle per wavelength. Now, the next is how we can map materials based on thermal variations. Now, different materials have different rates of absorption depending on the conditions prevailing in that particular area. They have different temperature absorption rates or heat absorption rates. In the night, their rate of absorption or their pattern of absorption of heat is different from their pattern of absorption of heat during the day, and this creates what we call the thermal variation effect. Now, we can use this property of thermal variation effect to map out the object of interest in that specified geolocation. So different materials have different absorption and reflection patterns, which results in thermal variations, and precisely in the environment where it's being recorded at a sensor level. Materials correspond to different temperature changes. This affects their thermal radiance. During certain periods in the day where temperatures are very high, some materials absorb a very significant amount of radiations, principally from the sun, and then they tend to reflect or emit these radiations when temperatures decline, and this phenomenon occurs at night. So these variations in the thermal radiance of the object instantiates what you call the thermal inertia effect. This is an apparent measurement of residual temperatures. The thermal inertia is a proportion of or is in proportion or direct proportionality with the thermal conductivity values and specific heat conductivity of the material. Now, thermal conductivity is a quantitative property that can be measured at the lab. But thermal inertia, that's apparent thermal inertia, cannot be measured from the images, but it's a qualitative property. So we can go from the known to find the unknown. That's the principle here. Thermal conductivity values are known. We can calculate thermal conductivity values for different types of materials in the lab. And once we get these thermal conductivity values, we can compare them to the thermal inertia images we've generated. This is simple, and it's a big advancement which can be relied on. So this thermal inertia, but in our case we are referring to it as apparent thermal inertia because It's a qualitative property, not a quantitative one. But thermal inertia is also significantly equivalent to apparent thermal inertia, which is directly proportional to the thermal conductivity, the density, and the specific heat capacity of the material. So this is the function that represents the thermal inertia. But the ones from the image we can get from the image is not necessarily the thermal inertia in the quantitative scale, but it's the thermal inertia in the qualitative scale. So but relatively they are the same. Once you measure those thermal inertias in the lab, they are the same as the thermal inertias in the images. But thermal inertias are really hard to find. So we can rely on the thermal conductivity value. Since the thermal inertia here is proportional to the thermal conductivity values, we can use simple proportionality to get the thermal inertia values in the images. Now, although we can't directly map thermal conductivities from materials from the remotely sensed images, but we can directly map the apparent thermal inertias of these materials and compare them to known standard thermal conductivity values, just as I've discussed earlier on. Now, these images here are clear examples of temperature variations. Just look at this geolocation here. This is a daytime temperature map for an area. Let's look at this geolocation here. Look at it, the changes that's occurring. This temperature here is a high temperature. The same spatial location, when you come here in the night, temperatures have dropped significantly. So it means that the material here, whatever material is found here, is absorbing radiations at different patterns at different times in a specified day. So we can rely on this anomaly to identify what objects or which objects it could be in the image based on their thermal susceptibility. Now this is a thermal imaging on Earth. Look at this object. It's really dark now in the day, but in the night this same object has a rim around it, that a radiant rim around it in the night. So it means that whatever is happening to this image, this object here in the daytime absorbs less radiations, but in the night time tends to emit more radiations. So that's the emittance here, and it's based on what the temperature radiance. So we can hinge on this behavior to identify the type of object or the type of material. As we discussed earlier on, apparent thermal inertia. Apparent thermal inertia can be calculated from the images. Then we calculate apparent thermal inertia using this equation, that 1 minus albedo over the changes in temperature times Nc. Nc are constants that can be omitted. They are relatively insignificant and they can be omitted in the calculation. Now albedo is the surface brightness. The changes in land surface temperature is the changes in the temperature, diurnal temperatures in the day and the changes at night. So the difference in those temperature regimes will help us find the change in temperature. Now, how do we calculate the land surface temperature? The land surface temperature, we can calculate the land surface temperature based on the type of satellite image you are using. If you are using Landsat 8, then this calculation is only restricted to Landsat 8. Now for Landsat 8, you use the ML. They are constants in the metadata of the image. So metadata of an image gives a summarized information about the image. So for Landsat 8, you can get these constants, the ML, the QCOL, the AL from the metadata. So this is what we call the top of atmospheric correction. So you have to correct your images here. Now once you are able to calculate for the top of atmospheric correction or the top of atmospheric effect, we can calculate for the brightness temperature. The brightness temperature, this is the equation, the K2 and K1. This L has been calculated for in the image, but the K2 and K1, they are constants from the metadata of the image. Particularly for the Landsat 8, you can get this K1 and K2 from it. Now once we are done with the brightness temperature, we calculate what you call the NDVI, the normalized difference vegetation index. Now we have vegetation in our area of work, and based on principle of photosynthesis, the radiations that are emitted from the sun, a proportion of these radiations are absorbed by plants for photosynthetic processes. So these plants use radiations, the solar radiations, they absorb some for photosynthesis. So we have to calculate this NDVI, the normalized vegetation index, the influence of vegetation on the temperature regime, then take it out of our calculation so that we can get the net residual of the temperatures hitting the land surface directly. So for that, we use in Landsat 8, we use the near infrared minus red band over the near infrared plus red band. So this is for the Landsat 8, the near infrared band is a band 5 and the red band is for band 4. Then so this is the equation. So band 5 minus band 4 over band 5 plus band 4. Once we are done, we have to calculate proportion of vegetation. So we are hinging on the normalized vegetation index to calculate proportion of vegetation. So we're using this equation. Sorry, this should be NDVI min, not NDVI max. So your normalized vegetation index minus the minimum of the normalized vegetation index all over the maximum of the normalized vegetation index plus the minimum minus the this is supposed to be plus the minimum of the normalized vegetation index all squared. So once you are done, you come to the next calculation. That's what you call emissivity. So the emissivity is 0.004 times the proportion of vegetation plus 0.986. So once all these parameters are obtained, we can calculate for the land surface temperature. The land surface temperature is the brightness temperature all over 1 plus this times the brightness temperature over this times the natural log of the emissivity. So for that, you can calculate for the land surface temperature for a respective period. Let's say in a day, you take the images in a day, then you calculate its land surface temperature. Then you also take the images at night for that same date. Then you calculate its land surface temperature for the night. Now the two, you do what you call the band math. You subtract the temperature in the day in those images from the temperature at night. So that gives you your temperature changes. Now we've talked about albedo. What do we mean by an albedo? An albedo is a property of the sun's energy budget. In simple terms, as we've discussed on the earlier slides, that some proportions of the emit reflected radiations don't get to the sensor level, but some are scattered and lulled in the atmosphere. This creates an inherent atmospheric brightness. So sometimes within a day, though the sun is very hot, but you can see that the weather is not bright. It means that there is low albedo. And sometimes the weather is hot and at the same time it's very shiny. That's what we call a high albedo. Now, how do we understand the concept of albedo? This is the 100% of incident radiations or solar radiations coming from the sun. Now, these radiations hit on the materials. The materials absorb some of these radiations, then reflect some of these radiations. So let's say 10% are being reflected. And out of this 10%, a proportion of this 10% are emitted to the sensor, and some proportions stay in the atmosphere, they scatter in the atmosphere. So this creates an inherent brightness in the atmosphere. So this is a low albedo effect, and this is a high albedo effect. So here we have 100% of the energy from the sun, and 80% is being scattered. So this creates what you call a high albedo. Now we can calculate how albedo using these equations, where band 1, band 2, band 3, band 4, band 5 can be obtained from the Landsat 8 series. We can get them and multiply them by these constants. These numbers are constants. So once you have the Landsat band 1, band 2, band 3, band 4, band 5, you can quantify the albedo. And once you obtain the albedo, you can plug the albedo here, then generate your new apparent thermal inertial map. Once you generate your apparent thermal inertial map, what you do is that you compare these apparent thermal inertias in the map you generated to known thermal conductivity values. You strike a relationship between the apparent thermal inertia, that's the thermal inertia, and thermal conductivity. You say they are proportional to each other. So once you know the thermal conductivity, you can infer the type of material in the map that you've generated based on temperature effects. So gravel has a thermal conductivity of 0.3 to 0.5. Basic granulate has a thermal conductivity as fixed, that's 2.2. Gneiss, or the garnet gneiss, has a thermal conductivity of 2. So once you identify a thermal conductivity or an apparent thermal inertia of 2, then it should tell you that the material there is a garnet gneiss. For norite is 1.19. So we can map these materials from the images based on these values. Then we are good to go. Let's also focus on understanding the electromagnetic spectra. Now, the electromagnetic spectra is made up of wavelengths of light or energy. It's just a representation of the wavelength of light or energy. So the window that describes the wavelength of light or energy, that's what we call the electromagnetic window or electromagnetic spectra. Now, our eyes can see within a restricted wavelength, and we call that restricted wavelength the visible spectrum. Our eyes can only see white light, and beyond or below that, our eyes can see anything off those wavelengths or off from those wavelengths. That's why people will say it's spiritual. Yeah, because we can't see with the physical eyes, so we become spiritual. That's not scientific. Now eyes can only see within 400 nanometers to 750 nanometers of wavelength of materials, either light or energy, whichever way you put it. Now beyond that, our eyes can't see beyond that. These are long wavelengths, the infrared waves, the low intensity infrared, radio waves, acoustic waves. They are long wavelengths and our eyes can't see in those regimes. Synonymously, our eyes can also see below 400 nanometers of wavelength radiation. So our eyes can see white light, which can be decomposed into the rainbow colors. It's very interesting. Let's continue. That's the electromagnetic spectra. Now this is a visible spectrum that our eyes can operate. That's a very minute window, and below or beyond that you can't see anything unless you use other devices and other mechanisms to see. In this you can see it's a long wavelength, 10 power 3 meters. We can see a house, baseball, a radio wave, micro. But in this ultraviolet, X-ray and gamma ray regime, our eyes cannot see them. We have to develop other sophisticated devices to see. Our eyes can see viruses because they are in the wavelength of 10 power minus 7. A light of wavelength of 10 power minus 7 can aid us see viruses. A light of wavelength of 10 power minus 7 can help us to view this. Likewise, proteins and water molecules. So this is also another image for you to look at and understand more of this electromagnetic spectrum. So as the wavelength is increasing, temperature is decreasing, and as the wavelength is increasing, the frequency of radiation is also decreasing. Now the intensity of emission, the emission is dependent on the intensity of radiation, not the frequency of radiation. So the photoelectric emission is dependent on the intensity of radiation, not the frequency. But the energy, the total energy of the photoelectron or the photons is a function of its frequency and the Planck's constant. You should be abreast with that. The next in line is the electromagnetic spectra for Landsat series. So once we've understood the wavelength mechanisms, this is just petty for you to understand. Now Landsat band 1, Landsat 8, the operational land imager, has 11 bands, and these are the respective wavelength of operation for each band. So Landsat 8, only 1 and only 2, their band 6 only operates within 1500 to 1700 nanometers. And the enhanced thematic mapper has 7 bands, but only one band, that's band 6, covers all the ranges in the thermal range or the thermal infrared. So that's that. The Landsat series, the operational land imager. We have the operational land imager Landsat 8 and 9. Now these are the wavelength categorization or the wavelength regime for each and every respective bands in the Landsat 8 and the Landsat 9. Then the next series of Landsat is this, where we have 25 bands. For the Landsat 8 and 9, it has 11 bands from band 1 to band 11. Band 1 operates in the visible range, that's the RGB coloration, that's the natural color. And band 8 is the panchromatic band that has 15-meter resolution. For this is the band 2, band 3, and band 4, that's the near infrared. And band 5, 6 are also within the shortwave infrared regime. Band 9 is for circles and cloud detection. 8 is in atmospheric correction. Then band 11 and band 10 are for surface temperature analysis, crop water use, that's the evapotranspiration calculation, cloud detection, and active volcanoes. So if you want to map active volcanoes using the Landsat 8 or Landsat 9, the useful bands will be band 11 and band 10. So in the next phase of the Landsat series, it will have 5 thermal infrared bands. That's band 21 and band 25. That will help you detect active volcanoes and also do land surface mapping and mineral mapping, just as we've discussed earlier on. Spatial and spectral resolution of satellite images. Now, spatial resolution is just the area coverage of the satellite image. The extent of coverage of the image is what we call the spatial resolution. Then the spectral resolution is the wavelength range of operation, the wavelength range in which these bands operate. So each band has a spatial resolution and a spectral resolution. So for the Landsat thematic mapper and the multispectral, that's the band 7 visible, the infrared thermal bands with 60 to 140 nanometer resolution. That's the spectral range, the wavelength range which it can focus. And the spatial resolution is 30 to 80 meters. Let's look at another multispectral image. That is the Landsat 7, the enhanced thematic mapper, which was launched in 1999. It has 8 visible, then infrared and thermal bands. Has 8 bands, has infrared, visible, and thermal bands, and operates within the wavelength range of 60 to 140 nanometers. That is the spectral coverage. Now for the spatial coverage is 15 to 60 meters. That's good. Now the lowest it can go is 50 meters, and the highest coverage it can go is 60 meters, which is good. Now when you look at a hyperspectral image like SPOT, it has 3 visible bands, the infrared band, which operates in the spatial range or spectral range of 70 to 100 nanometers. Now the spatial resolution is 10 to 20 meters. It means we can get fine details, explicit details from these images. So it depends on what you want to do and the image available. So if you want to do detailed mapping, when you have to get keen information, sensitive information, then you have to go for a band that has a very sharp spectral resolution When I say a very sharp spectral resolution, it means that the area coverage is very small, so we can get more details. And a very sharp spatial resolution means that the spectral range is very skewed to that range, where you can get the information of that particular object you want. So for the Aster metadata, Aster has 14 bands. 3 bands are in the visible near infrared ranges, and these 3 bands they have a spatial resolution of 15 meters. For the shortwave infrared has 6 bands from band 4 to band 9 with a spatial resolution of 30 meters, and the thermal infrared has 5 bands with a spatial resolution of 90 meters. So when you are doing something like vegetation studies, this will help you get fine details about the vegetation. And for thermal studies, where you want to map active volcanoes, means it's operating within the range of 90 meters by 90 meters. If it's a square pixel, it's a 90 meters by 90 meters. And this is the range of operation. On the other hand is the Landsat series, where you know the spatial resolution, the spectral resolution of each and every band in the Landsat operational land imager series. So for the Landsat band 1 is the coastal aerosols. This is the spatial resolution, spectral resolution, and this is the spatial resolution. The band 2 is a blue band, band 3 is a green, band 4 is a red band. They all operate in a spatial resolution of 30 meters by 30 meters pixels. Then the band 8 is a panchromatic band, which is 15 meters. Now, I am introducing you to a concept where we are going to discuss it in the next slides, but it is a concept of what you call the pan sharpening, where we use a highly spatially resolved image to enhance a lowly spatially resolved image. For example, in the Landsat series, we can use the panchromatic band to enhance other bands like the band 2, band 3, band 4, and band 5. Those that have what? High spatial resolutions. We can use the low spatial resolution bands to enhance them. We are going to talk about that in the next series of slides. Okay, we are here. Spatial enhancement. Now, spatial enhancement. The spatial resolution of satellite images can be enhanced from a high spatial resolution to a very detailed spatial resolution. This is made possible by the principle called the pan sharpening. So in pan sharpening, a band with a smaller spatial coverage is used to modify bands with high spatial coverages. For example, in Landsat 8, the band 8, which is a panchromatic band with spatial resolution of 15 meters, can be used to enhance other remaining bands to help in detailing out information in the band with great efficiency. So let's say you are using the shortwave infrared bands, which has a spatial resolution of 30 meters. Now we want to break down and get fine details at a level of 15 meters by 15 meters. All what you have to do is that you have to pan sharp the shortwave infrared bands by using the band 8, which is a panchromatic band with a very enhanced spatial resolution of 15 meters. There are variants of pan sharpening algorithms where we can rely on to reduce our spatial resolutions of the images. First is the Gram-Schmidt, second is the color normalization, then we have the N diffuse, we have the Throws wavelength transform, we have the discrete wavelength transform, we have the Brovee, the principal component analysis. The theory of spectral signatures for remotely sensed images. Now, what do we mean by spectral signatures? Spectral signatures are unique or diagnostic features of a material in the electromagnetic spectrum. Just as we discussed earlier on that our eyes can see some materials because our eyes operate within certain wavelength of electromagnetic radiations. So our eyes are only keen to these materials because that's the wavelength operation of our eyes. So spectral signatures are diagnostic features of a material. Now, once the light rays are incidented on a material, as discussed on earlier on, depending on the molecular structure of the material tend to absorb certain radiations at certain frequencies or wavelengths and emit certain radiations. So that's the principle of spectral signatures. So for that particular material, until that respective wavelength or that particular wavelength is reached, that material won't absorb that. Or if that light ray coming is devoid of its wavelength of absorption, that material won't react to the radiations coming. It will remain idle. So once the radiation coming is embedded with its right wavelength of operation, then the material is going to respond to that radiation. So many materials have different or have unique characteristics of spectral properties with a significant amount of electromagnetic radiations reflected or absorbed at particular wavelengths, which can be used to identify them with a high degree of confidence. Different mineral groups have distinct chemical behaviors and hence portray distinct responses, either absorption or emission, or that's reflection, to the light rays or specified frequencies that are incident on them. The incident rays stir up atomic vibrations, which gives rise to preferential absorptions at different energy transition levels. So the light rays coming or the incident rays coming, when it hits on the object, it stirs up what you call atomic vibration and gives rise to what preferential absorption. So once the wavelength of that material, the wavelength of absorption of that material is within the range of wavelength in the incident radiation, the material will preferentially absorb that wavelength, then emit the rest, the residual. So at that critical wavelength, we say the spectral signature of that material is found at that wavelength. So when you have a wavelength of 2 nanometers, let's say for a material, let's say a rock material that has a mineral like opal, and say the opal has an absorption wavelength of 2 nanometers. Once the light ray coming has a spectrum of wavelength of which 2 nanometers is recorded in it, then opal is going to react at only 2 nanometers of wavelength of incident radiations. So it tends to absorb those wavelengths and emit the residual. Critical absorption wavelengths are analogous replication of chemical responses of these different mineralogical groups. So the critical absorption wavelength is a replication or is diagnostic of the chemical responses of these mineral groups. So in this image on the right, we can see that the absorption, the deepest absorption wavelength of smectite is around 1.4 nano 1.4 micrometers. That's smectite here. So at 1.4 micrometers, we say is the spectral signature of smectite. Then halite plus smectite here has the deepest absorption around 2.2. So that is the diagnostic property of halide. Now, another concept where we have to understand is that a material can have a multi-phase of absorptional spectra or multi-phase of absorptions. It can absorb different or it can absorb at different episodes of wavelengths. So for that material, it is not going to have a diagnostic property. But for everything on earth, it has a unique property to identify it. Although it can have different absorption rate, but there is one absorption rate that is going to help us identify that material. So it could be that the material has about 4 phases of absorption, but there is only one that is very peculiar to the material. So we have to find that one, and that one occurs at what we call the deepest absorption range. So you could see here that smectite, here in this image, smectite has 3 absorptions, but the deepest absorption is around 1.9 micrometers. Halide as well has 4 different absorptions, but the deepest absorption is around 2.2 micrometers. Same can be said of halide and smectite together. So the deepest absorption of halide and smectite in composition is around 1.9. So you could see halide and smectite exhibiting different phases of absorption, but there is one key absorption that signifies them, and it happens at what you call the deepest absorption. Now, this is also what you call the spectral signatures for other minerals. For hematite, goethite, jarosite, all what you have to look out for is the deepest absorption. Where does the deepest absorption occur? And these are the bands for the Lancer series. So we have the band 1, band 2, band 3, band 4, band 5. They are wavelength operation, or their wavelength range. So band 7, this is the wavelength of operation. And for the deepest absorption for jarosites, we can get, if we want to correctly map jarosites, we have to rely on band 7. So because that is where the deepest absorption for jarosites occur. Now hematite, we have to also look out for the deepest absorption in terms of reflectance. Now it's around this range. So if we want to get hematite, then we have to principally rely on band 3 and band 5, because this is the deepest absorption, this is also a deepest absorption. So we can use band 3 and band 5 depending on the mechanism of operation to map out hematites. How do we acquire spectral signatures? Now we can acquire spectral signatures using these approaches. The band rationing, that's the division of bands based on their absorption and reflection behaviors. So this principally generates a grayscale or shades of gray resultant image. We also have the false color composite. We have the band differencing, the RGB band color combination. That's a technique where we combine different bands to enhance the effect of a material. So for the band rationing approach, you have the Crostal technique, you have the Sabin's ratio and the Kaufman's ratio. They are all for mineralogical studies. Now we also have the predetermined spectral signatures. You can have some known or some laboratory generated spectral signatures sitting in an archive. So we can go to those archives and retrieve those spectral signatures to help us map our mineral of interest. So some known spectral signatures of some materials can be obtained with what you call spectrometry or spectrometer at the lab. A collection of spectral signatures is what we call N members. So this image is a collection of spectral signatures for jarosite, goethite, hematite. So we say that this image is a collection of the N members. So it's an N member sequence. So we are collecting different materials, the spectral signatures of different materials. Then we put them in one umbrella or put them under one umbrella. So these are what you call the N members. So we store these N members in what you call the spectral library. So wherever you store it is your spectral library. Now, sources of spectral libraries, we have the user-defined spectral libraries where you customize your own spectral libraries and you save these spectral N members in a library. Then we also have the standard spectral signature archives. That is the USGS spectral library for multispectral images, both for Landsat and ASTAR images. So when you go to these archives, the USGS spectral library archives for multispectral images, you can get spectral N members for different types of minerals. That will help you use them to map out the minerals in an image for an area. Now, we are coming to the basic band operation. How do we operate bands? How do we analyze bands? How do we calculate within bands? We have what you call the band math. It's an algebraic operation that is performed on the bands provided the underlying argument is valid. So in real terms, it's what you call the raster calculation. So we can add, multiply, divide, square, exponent bands. So it's called band math, the raster calculation. You can do any form of operation with bands. You can divide bands, multiply bands, subtract bands, add bands, exponent bands, log bands. You can all do them at once, provided the basic argument, the underlying argument is right. There are no zero values. So when you are dividing a band that has numerical values, non-zero numerical values, by a band that has a zero numerical value, you should expect what you call a math error. So you make sure that the bands you are dividing is a non-zero band. You divide non-zero, the numerator bands and the denominator bands. Specifically, the denominator bands does not bear any zero value. We also have the trigonometry operation. Then have the conditional operation where we use the Boolean logics and the fuzzy membership operation. These are operations where we are going to look at them in a practical section. Now, spectral signature enhancement. How do we enhance spectral signatures? We use the band ratio. We've talked about spatial enhancement where we use the lower or the highly resolved bands to enhance the lowly resolved bands. So just as we can do spatial enhancement for an image, you can also do spectral enhancement. You can enhance the spectral signatures. Sometimes the images have correlations, high correlation effect. Certain materials tend to be correlating to certain materials depending on the closeness of the wavelength of absorption of these materials. Some materials have close wavelength of absorption. So in a raw image, you can't distinguish one material from the other unless you do enhancement at a spectral level. So we also have the band ratio. The band ratio is also for spectral enhancement. We have the linear contrast enhancement, we have the spectral filtering, histogram quantization or equalization, we have the principal component analysis, the MNF, that's the minimum noise fraction, then the independent component analysis, that's the ICA. Now for band rationing, it's just the division of pixels in one band by their corresponding pixels in another band. It is basically used to enhance the differences in brightness between bands which represent identical spectral features while suppressing other features. That's shadowing caused by topography. So we used to enhance the band ratio can be used to enhance one feature over the other. Some materials have close spectral absorption rates or absorption ranges. So once we can't distinguish them at a raw stage. So once we are able to do a band ratio or do a spectral enhancement, one of the materials is enhanced over the other. So one of the materials tends to stand out spectrally. That's what we mean by enhancement. So in band rationing, the resulting image will always be in gray scale, that's monochromatic. In order to know the exact spatial location that holds the material that's the meaning of interest, depending on the band ratio, we must always be on the lookout for bright pixels. So if you want to know the special signature of the materials enhanced in the band rationing process, you have to look out for the bright pixels depending on how you divide the band. Sometimes you can fall onto the dark regions depending on how you divide the bands. So if I want to identify iron oxides in the Landsat series, I'll use band 4 over band 2, and the resultant image I'll check for areas that have what? Bright pixel signatures, and these will be my areas bearing iron oxides. Conversely, when I turn the band ratio approach and make it band 2 over band 4 for iron oxides, I am looking at dark regions in the image. In principle, the more brighter the ratio is, the better the certainty of finding our material or mineral of interest. So the brighter the pixel stands out from the band rationing effect or the enhancement effect, the more explicit you get information about that mineral or material of interest. We have some issues with remotely sensed images, basically due to topography, the effect of topography. You know, the satellite is positioned at a certain angle, and sometimes the nature of the topography of an area can offset the radiations going back to the satellite. So topographic effects can also have their consequence on the images acquired. However, all these have been factored prior to the delivery of the images. So we have the topographic effect correction being factored in. Then we also have seasonal variations that affect the sun's illumination. That's the humidity, cloud cover. All these ones also affect remotely sensed images. The other one is vegetative cover. Sometimes we are not looking to analyze vegetation. Our materials are covered by vegetation. So how do we get that effect out of the image? So there are other correction mechanisms on the image. We have to pre-process our image to take out the effect of humidity, the effect of clouds, the effect of cloud cover or vegetation cover, sorry, then the effect of topography. We can do them. So we correct our image. Now let's look at how we do the band ratio, the practical aspect of it. Now, this is an image. An image is dimensional. It could be a rectangle or a square. depending on the dimensions we pick. But in each image, there's a segmentation where we divide the image into smaller areas, and each area is what we term as a pixel. So a pixel is just an area coverage in a large image. So and a pixel covers a row and a column. So for the rows, it depicts the dimensions, the lateral dimensions, and the columns depict the vertical dimensions. So this side can be maybe 20 meters by, this is a rectangle, 20 meters by 10 meters. So that's the pixel coverage. But mostly we use a square coverage, so 20 by 20 pixels. So that's why you say 20-meter resolution. So this is also going to be 20-meter resolution, 20-meter resolution. These are the dimensions. But aside that, each pixel holds an information based on the absorption rate of the material it encountered. So each pixel has what you call digital numbers representing the information about the materials of interest or the materials that were able to absorb light or the incident radiations. So these are digital numbers. So likewise, this band, this spectra or this pixel geographically corresponds to this pixel in geographic context. So when we are doing the band ratio, when I'm dividing band 2 by band 1, this digital number will be divided by the digital number here. When I'm doing band 3 by band 2, this digital number here will be divided by the digital number here. But anyway, we are not going to work in digital numbers. These digital numbers, they are raw values. They are not spectral values. They are not wavelength values. So it's just a coded aspect of it. But when we are pre-processing the image, we have to do what we call corrections. We have to convert digital numbers to spectral numbers. Now let's look at some mineral band ratios for Landsat 8. Now for Landsat 8, for us to map ferric ions, that's redness, in a Landsat 7 enhanced thematic mapper plus, we use band 3 over band 1. For band 3 over band 1, we check the bright pixels. But that is different because the wavelength of operation of Landsat 8 is different from the wavelength of operation of Landsat 7 as discussed earlier on. So for Landsat 8, if we want to map ferric ions, we are going to use band 4 divided by band 2. Then ferric ion 2 in the Landsat enhanced thematic mapper plus is band 3 over band 1 times band 3 plus band 5 all over band 4. That also changes in Landsat band 8. So as we know, band rationing is the division of pixels in one band by their corresponding pixels in another band. In band rationing, the resultant image would always be grayscale, that's monochromatic. In order to know the exact spatial location that holds the material of interest, depending on how you divided the bands, we must always be on an outlook for the brighter pixels. In principle, the more brighter the pixel is, the better the certainty of locating our material of interest. The numerator band represents the band pixels with absorption features. So here, like band 4, so band 4 is the band with absorption features. It's the absorption band for iron oxide. Iron oxide is absorbed in band 4 in the Landsat 8 and is reflected in band 2. So the band 4 is the absorption band and the band 2 is the reflection band. So iron oxide absorbs in the Landsat band Landsat 8 band 4 and reflect in the Landsat 8 band 2. So always look out for the absorption and the reflection bands. Once you divide them in the right order, generally go and look out for the bright pixel or bright pixelated areas. So this is another form if we want to map clay minerals in Landsat band 8. For clay minerals, specifically culminates, it's band 7 over band 5. That is band 7, which is the absorption band for clay minerals, and band 5, which is the reflection band for clay minerals in Landsat band 8, in Landsat 8 images. Then if we want to map multimilronite, is band 4 plus band 6 all over band 7. It means that the composite effect of band 6 and band 4 are the absorption. So clay minerals like multimilronite has two deepest absorption, which occurs in band 4 and band 6, but it always reflects in band 7, wavelength range of band 7 in the Landsat band 8. Carbonates, if we want to map carbonates like this, specifically calcites, is band 7 plus band 9 all over band 8. So the numerator band or the numerator operation is for the absorption bands and the denominator operation is for the reflection bands. So likewise, we can also hinge on this one in the Landsat 7. This is Landsat 7 to map these minerals. For band 3 over band 1, we can check out for the brighter areas to map out iron oxides. For magnetite, that is iron 2 and iron 3 content, you can use band 5 over band 1. For hydroxyl bearing minerals and clay minerals, you can map them using band 5 over band 7. For metal volcanics, which is band 3 over band 4 times band 5 over band 4, you can map metal volcanics. Limonites can also be used in this way. This is the band ratio operation. Now, Landsat 8 band ratio, band 4 over band 2, we use them to map iron oxides. Band 6 over band 5 used to identify ferrous minerals, that's iron bearing, other than iron oxides such as amphiboles, pyroxenes, and olivines. These effect results as a result of the high absorption in band 6 and reflection or reflectance in band 5. Band 6 over band 7 used to identify hydroxyl bearing rocks, and band 7 over band 5 is to identify clay minerals in the Landsat band 8 series specifically. So these are also other way. Now we also talked about RGB, where we combine bands, we stack bands together. Now these band ratios, band 4, we've divided these band ratios, band 4 over band 2, band 6 over band 7, band 6 over band 5. We can stack them together, combine them together to give us a composite effect. This is used to generate hydrothermal alteration maps of lithological features, and this approach is what we call the Sabin's ratio. Then for Kaufman's ratio, to discriminate altered rocks and lithologies from vegetation. So sometimes in the image is highly vegetated, we can't see the rocks and we can't see alterations. So we use this Kaufman's ratio to reduce the effect of vegetation and hence pick out our lithological and alteration units in the area. So this band ratio, this is a combination of band ratio and RGB colorations or RGB stacks. We use these ratios stacked together to discriminate altered rocks and outcrops from vegetation. So we can go through all these ones here for the Landsat series. That's the band ratio. This is the band RGB color combination. If you want to discriminate structures, lithologies and vegetation, this RGB 543 combining them in the same order can help us distinguish mafic, ultramafic rocks. Now the mafic and ultramafic rocks will appear greenish in the resultant image, or greenish brown in the resultant image, whereas vegetation appears to be red. Now once we combine band 7, band 5, band 3, we can use them to map ultramafic and mafic rocks in pinkish brown colorations. The gneiss will appear in blue. Also, band 7, 5 and 2, ultramafic and mafic rock or mafic rocks will appear pinkish, whereas gneiss appears to be blue in coloration. So once you see the image, you do this RGB color combination and you see blue in the resultant image, it should tell you there is gneissosity. That area has undergone gneissosity. Now, band 10, band 6, band 7 for Landsat 8, gneissic areas or granitic areas will appear green, whereas mafic areas appears pinkish. Band 11, 7 and 6 combination gives gneiss and granitic areas in blue colorations. So it goes on and on. Now this is also the band ratio coding for using ASTAR data. So if we want to map alunite, culminate and pyrophyllite, we use band 4 plus band 6 all over band 5 in the ASTAR data. Then carbonate, chlorite and epidotes is band 7 plus band 9 all over band 8 in the ASTAR data. Muscovite is band 7 over band 6, then hinged is band 5 over band 6. If we want to map quartz abundance, the abundance of quartz, that's what we call the quartz index. In the ASTAR data, we use band 13 over band 10. Can really tell us the quartz bearing rocks. So you look out for the brightest areas when you divide band 10 by band 13 by band 10. The brightest areas, the purest, brightest areas represents quartz. Mafic index, if you want to map mafic units in the ASTAR data, use band 12 over band 13. Carbonate index, band 13 over band 14. Then if we want to map oxide bearing altered rocks, use this equation. So these are also the RGB color combination for the ASTAR data. So band 4 over band 7 for discriminating serpentinites or serpentines from talc carbonate rocks. Then band 8 also shows the contrast between iron-rich rocks of mafic and ultramafic affinity, which are mapped as bright pixels, and also helps to distinguish island arcs, metavolcanics, gabbro, all in moderately gray pixels, then granitic intrusions as dark pixels. Then this RGB color combination for band ratios of these bands is used to highlight mafic to ultramafic rocks as well as gabbro diorite intrusions from the background rock unit. It clearly helps to distinguish the amphibolite as well as carbonaceous schist in the steady area. These are the reference authors, so we can hop onto these people and dissect their works. So further, these are also for ASTAR data. So for ASTAR data, if you want to discriminate sulfide rich areas, this is the RGB. You combine band 12, band 5 and band 3. If you want to discriminate between silica, carbonates, mafic or mafic and ultramafic rocks and gypsum, you are going to use these RGB color combination with a band ratio product. So gold sands, alterations and host rock. For gold sands is band 6, then alterations band 2, then host rock is in band 1. These are all reference authors. Now, some vegetation band ratios. Now we discussed how can we, there are vegetations, there might be vegetations in our area of work or area of interest. How can we suppress the influence of vegetation? Now these are vegetation indices to help us do that. So we have the difference vegetation index, the soil ratio, the normalized difference vegetation index. You can have the water index and others, so on and so forth. All these are in respect to Landsat 8 satellite image. Now, how to assess the uniqueness of N members, as discussed on that N members are a collection of spectral signatures. So we collect spectral signatures, but how to assess them? How unique are these spectral signatures? How unique are they? So oftentimes different minerals or different materials exhibit similar spectral traits within the electromagnetic spectrum, which takes them or makes them very, very tough to differentiate. That's distinguishing one mineralogical group from the other. Hence, it's very prudent to assess the uniqueness of these composite N members for the sake of clarity. In this regard, there are some indices which will help differentiate pixels from its surrounding neighbors in the same spatial regime. These indices help to quantify the extent of similarity of a pixel in relation to its contiguous neighbors. Now, certain materials have closeness in absorption features, so their spectral signatures are a bit identical. If you don't take care, you might misuse them. So you have to find a mechanism of identifying how unique a spectral signature or spectral signatures are from their counterparts. So that's all what it means. So in a contiguous space, due to the closeness, certain features can exhibit the property of certain features. It depends on how close they are. So we have to suppress one feature and exonerate one. So these indices are the spectral purity index, spectral unmixing, spectral separability, and spectral filtering. So you could see that here in this photograph, these spectral signatures, this group of spectral signatures are different from this group of spectral signatures. Initially they were jumbled up together, but now they've been distinguished based on their properties. So we use different algorithms to distinguish these spectral signatures. So one of these mechanisms is what you call the purity index through the n-dimensional visualization. Now, pre-processing of remotely sensed images. how do we process our really sense image? Once you get the image, what do? Now the image comes in tiles. They come in different areas. Let's say for an area, one particular area, you can get 3 or 4 different images. You have to mosaic them. You have to join them in contiguity. Now once you join them, you merge them to one complete file or one complete image. Maybe your area of interest will be a tiny portion of those joined image. What you do is that you do subsetting. You subset your area of interest from the mosaic image. Once you subset your area of interest, this helps to reduce computational time, because when you have a large mosaic image, the processing time is prolonged. So once you subset your small area of interest, the area you are going to work within, it gives you a sizable image which reduce computational time. So after your subsetting, you do what you call radiometric correction. That's the image in the raw form has digital numbers, just as I showed you in the previous slides. It has digital numbers. So you have to convert these digital numbers to surface reflectance or reflection or radiance. So you convert digital numbers to surface radiance or surface reflectance. That's what you call the radiometric correction. Then you do the next activity in line, that's atmospheric correction. You correct the images, the effect of atmosphere in the image. So for the atmospheric correction, we have different types of algorithm. We have the flask, we have the QUAC, we have the dark band subtraction. Then you remove clouds. It's very necessary if there are a lot of cloud cover in the image you obtained. You have to remove clouds. Then we do snow removal. Then we do bad band correction. Some of the bands are defective, so we remove them. They come with scan lines. Scan lines are just lapses. Some of the areas the satellite couldn't cover it or couldn't capture images from that area, so those areas are left blank. Or sometimes due to operational defects, the images for that area couldn't be processed, so there will be lapses. So you have to fill those lapses. And sometimes the images can be expanded to involve these petty errors. So you have to remove these bad bands. Then also remove the scan line. Then we do thermal correction, the temperature in the image. The thermal correction also come in relation to what you call the albedo effect. A lot of surface radiations in the image, so you limit the albedo effect. That's why we do the thermal correction, because once the radiations are scattered in the atmosphere, it increases surface temperatures as well. So then the next itinerary is layer stacking. Stack the layers. So let's look at this is our atmosphere, these are the satellite in space, this is our earth. Look at the cloud cover. So imagine your satellite is positioned here. How can the satellite penetrate to get information through this cloud? Although it's radiation based, but this cloud has to be corrected. So there are lots of algorithms to correct this cloud cover so that you can enhance the features of the material in question. Now let's come to target mapping. How can we map our materials? Now the materials, when we did the band rationing and we did the spectral M-member collection, we collected them for limited areas. We didn't collect them through all the entire area. We collected them for limited areas, because when you have a large image, you can't be collecting spectral signatures for all the images in every pixel. It takes a lot of time. So all what you have to do is that take the spectral M members that you collected and place them in a library, take them and now develop an automatic way to let an algorithm use these spectral end members to maneuver through the images. Now automatically map out the rest of the areas where you couldn't identify with the spectral signatures or the end members collected. So that is the functionality or the assumption or the main idea in target mapping. So target detection is an automated mapping procedure in which all the identified discrete spectral signatures relating to the images are used to assess the entire region of interest. In mapping, the collected spectral end members are used to find patterns, that's to make classifications over the entire region of interest using image processing algorithms. The image processing algorithms are spectral based or machine learning based. That's either supervised or unsupervised. That's machine learning comes in two folds. It's either supervised, unsupervised, or reinforced learning. So the spectral based algorithms are invariants. Likewise, the machine learning algorithms. So these spectral signatures, that's the end members, are collected via pixelation. So you pixelate to collect these end members. So for every spatial region, for every pixel, you collect the spectral signatures you can identify via the band ratio or the RGB color combination. Collect them within a pixelated area, then you store them in your spectral end member archives. Now, like this one, this area is a collection. We've collected the spectral signatures for a limited pixelated area. Now you automatically hire the exigency of different number of automatic mapping algorithms to help you classify the entire image depending on the prevailing or the available spectral signatures you were able to obtain from the image. So this process becomes what you call automated target mapping. Now you can see here you collected maybe few spectral end members for limited spatial regime or spectral area, but they were able to classify the image completely using these spectral signatures without having to stress yourself to collect spectral signatures for each and every pixel in the entire image. Now, target detection mapping algorithms. We have the supervised algorithms, that's the spectral base. For the spectral base, we have the spectral angle mapper, paralleloparallel, we have the spectral information divergence, the constraint energy minimization, the spectral feature fitting, and the spectral match filtering. For the machine learning approach, we have two. We have the supervised and the unsupervised aspect as well. For the supervised, random forest, artificial neural network, extreme gradient boosting, stochastic gradient descent. We have the group data handling process. We have a tree of decision making of this. We have the family of decision making trees. Then we have the nearest neighbor, the k nearest neighbor algorithm. Support vector machines. We have a ton of them. A ton of them. Then the unsupervised one, we have the ISO data. That is the iterative self-organizing data analysis technique. We have the hierarchical clustering, the fuzzy C means, the K means. We have the T stochastic neighborhood embedded function or the neighborhood embedded algorithm. These are all unsupervised clustering algorithms. Now, this is a flowchart of satellite imaging process, specifically in mirror mapping. What you do is you get your hyperspectral or multispectral data. You do the data pre-processing where you do the mosaicing, you do the subsetting, atmospheric correction, thermal correction, cloud correction, bad band removal. You do all these things. Now, what you do is you come back, okay, you discuss your pre-processing, you do the radiometric calibration, atmospheric correction, bad line removal or black line removal. Then you do dimensional reduction, that is, you reduce the dimensions. Some of the images have correlated effect of materials or properties, so you have to make them uncorrelated. And these two algorithms, the minimum noise fraction and the principal component analysis, are for decomposing your images to uncorrelated facets of information. Once you are done, you can do your RGB color combination, that's the first color composite, or the band ratio. Now, the next activity here is to do the n-dimensional visualizer to assess the purity of your pixel. Now, once you're able to assess the purity of your pixel, you do the n-member collection. After the n-member collection, you do your spectral unmixing to check how differentiable these spectral signatures are. Once it's done, you go to your target detection process. For the target detection process, we have the spectral angle mapper. You can use the spectral approach or the machine learning approach. Depends on your desire. So once you are able to do the automatic image mapping, you get your raw image or the final image. Once you have your final image, you do what you call ground truthing. You pick certain areas randomly from your generated automated map, then you visit those areas and see if the information you were able to map using the algorithms corresponds to the information on ground. So this is also a compounded form of processing your image data. So we look at your data, you can get the Asta, the Landsat 8, the Pulsar, the Sentinel 1B. You pre-process your data, you do the radiometric correction, atmospheric correction, flash algorithm, the layer stacking, the resampling, that's the pan sharpening. You can also do auto rectification, adaptive leaf filtering, mosaicing, and subset layer stacking. Then you come to the third phase of the pre-processing or the process: band ratio, spectral indices, principal component analysis, thresholding of ROI, exporting shapefile. Then you do your band math, RGB, directional filtering, line extraction algorithm. You export shape files to what? ArcMap. Then mapping, your mineralogical and lithological mapping, then visual and automated structural mapping. So what are the file formats of the images you acquire or the resultant images you can generate, or the file format of the images you are going to use? Mostly we use GeoTIFFs and files with .dat extension or HDF header files or text files, particularly for Landsat metadata. For Landsat metadata, it's in text files, so you can open them using your normal text file operator. Then we have the HDT and JPEG and the PNG. Let's look at sources of multispectral images where we can get satellite images. So for the Landsat 8 and 9 operational line imager and thermal imaging or thermal infrared images, they are multispectral. They have 11 bands with spatial resolution of 30. These are the source. Go to Earth Explorer USGS Gov, get them. They are free of charge. They are open source. So for Sentinel-2 imagery, it's multispectral. It's good for mirror mapping and what? Vegetation mapping. This way you can get them from Earth Data and Earth Explorer or even Copernicus. Asta 1B is good for geological studies. For multispectral, has 14 bands with spatial resolution of 15. This is the source you can get them from. Then EO1 Hyperon or EO1 Privilege, they are hyperspectral, so you have to pay to get them. And in Ghana here, it's available for only the northwestern portion. We have the Average, good for mineralogical and soil studies, hyperspectral, it has 224 bands with spatial resolution of 20 meters. We have the Upview 3, good for mineralogical and soil studies, hyperspectral, has an equivalent of 50 spectral bands and less than 1 meter spatial resolution. These are software licenses. What software do you need and how to acquire them and the price involved in their acquisition. For geomatical core, that's commercial software, this is the cost involved and this is where you can get them. You can email them to get the software. Then you have the Ezra ArcGIS Pro, is commercial for geospatial and geostatistical analysis. You can use them to also process remotely sensed data. It's unavailable, so it's a franchise. In Ghana here, that's where you can get them. Samples Geospatial Limited Ghana. And Harris L3 Harris Geospatial NVI software. It's a commercial software where you can get them. It's good for satellite image processing and manual target identification. Then Quantum GIS is an open source, it's free of charge. You can get them. So this is a beautiful RGB raster image displaying various spectral features of different materials. It's very nice. So thank you. Thank you for staying along. The next phase of this tutorial is a practical section where I'm going to compound all what we learned and throw them into the practical section for you to understand what we mean by how to process the data, how to acquire the data, where to acquire the data, which processing do you make, which intuition do you make, the contributions you make from the data so that you can get a holistic map and now move on to the next phase of your prospecting campaign. So thank you. This is Infinity Geospatial. My name is John Osukonde. I am the CEO of Goodwill Geospatial Consult. Thank you for spending your time to watch this video. I hope you like, share, and subscribe to this channel for more exciting and intriguing videos on geospatial data analytics, particularly for mineral mapping and geoscience purposes. So thank you once again. Gracias.